Hello everyone and namaskar. In this video, we are going to talk about how to implement basic gates, universal gates, and special gates using our transmission gate. So in our earlier video, we have discussed about what is meant by a transmission gate and how actually it works. So let us start. So the first gate that we are going to implement will be our AND gate. So first of all, we'll draw its truth table and then we'll see its implementation. So for the truth table, as we know, we will have two inputs, namely A and B, and at the output side we can check as Y. So as AND gate is nothing but the product of two quantities, so we can get the result as 0, 0, 0 and 1. Now based on this particular truth table, we'll see how to implement this using the transmission gate. So for the transmission gate, we have a parallel combination of PMOS and NMOS. So let's draw the structure. So this is our schematic of a PMOS and NMOS connected in parallel with each other. Now if you see, this particular transistor is being controlled with the inputs as B. That is nothing but complement here B bar, and this is B, and the same is connected over here and here as B bar. So we can add the isolated terminal and this is our complement. Okay. Now as you know, one of the input is going to be the control input, so we'll be controlling this with the help of B. Now why you are using B? Because it changes from 0 to 1, 0 to 1 and 0 to 1. So as it is toggling, so it is working as a control signal. Now the question arises, how can we accumulate A? So let's come across the truth table. Now from the truth table, if you see, B could have two different combinations. Either it could have 0 value or it could have 1 value. Now whenever we have B as 1, let's start with this. Whenever we have B as 1, our output, if you see, here the output is 0 and here the output is 1. Now from where it comes as 0 and 1, so let's come across A. So here if A is 0, our output is 0, and if A is 1, the output is 1. So we can derive one condition from this as when control input B is equal to 1, output Y will be equal to A. So if it is 0, we'll be getting 0. If it is 1, we'll be getting 1. So for that case, let's start with the first combination. Here it is. When B is equal to 1, B bar becomes 0. 0's complement will be 1 and this particular transistor will be turned on. So for that, we'll connect input as A. Fine. Now let's come across the second condition as when B is 0. Now what happens when B is 0? See it here. If B is equal to 0, here we'll be getting complement as 1. So here logically 1. And when B is equal to 0, your B bar will be 1. Now if B bar is 1, again here logically 1. So this particular transistor will turn on. Now if this is turned on, let's come across the truth table. See this condition. When B is equal to 0 and when B is equal to 0. Now for both this combination, if you see the output is fixed. That is nothing but what? 0. Here also 0 and here also 0. That means when B is equal to 0, Y is fixed. That is nothing but 0. So we can connect this particular transistor with input as ground. So when this is turned on, your output will be 0. If this is turned on, output will be A. And these two will connect to the output terminal as Y. So this particular circuit shows the implementation of AND gate using the transmission gate. I hope you understood, and let us use the same concept for the remaining gates. Now I have written here the second as OR gate. We know the truth table as it is nothing but an addition. 0 0, it will be 0, 0 1 1. For 1 0, result is 1, and for 1 1 also the result is 1. That means for all these three combinations, our output is going to be 1. Now let us derive a conclusion based on which we can implement using transmission gate. Now again we can use the control input as B. Now see the condition. When B is equal to 1, we can see this particular scene. Now when B is equal to 1, if I come across the output is 1. So there is no dependency on A. So we can say when B is equal to 1, our output is fixed as 1. Counterpart, when B is equal to 0. Now we'll see this condition. Now when B is equal to 0, this and this combination, for both these combination, you can see output here is 0 and here output is 1. That means it could be dependent on A. Let's see A. Here A is 0, output is 0. Here A is 1, output is 1. So when B is 0, shall we write Y is equal to A? Yes, exactly correct. So if A is 1, output is 1, A is 0, output is 0. So based on that, let's draw. This is a first gate. Let's connect this with B bar. Again the second one. This is with B and this is with B bar. Output is Y. Now let's. So here when B is 1, this transistor is on. It is connected with logic 1. Logic 1 is nothing but high voltage. We'll connect this with VDD. Second, when B is 0, as you know, this transistor will turn on, connected with logic A or input A. So this is connected with A. So based on that, we can see OR gate is implemented. Now let's come across the third as NAND gate. So the truth table, as we know, NAND gate is the complement of AND. So we can write 0 0 1, 0 into 1 0, complement 1. This is 1, and for 1 1 it will be 0, just complement of AND gate. So let's come across the conclusion. First, when control input B is equal to 1, so we have two cases, two combinations, this and this one. So if you see when B is equal to 1, your output is 1, and when B is equal to 1, the output is 0. Now is there any relation with A? Yes, for sure. How it is? If this is 0 and this is 1, that means it's complement, right? This is 1, this is 0, it's complement. So we can write when B is equal to 1, Y will be equal to A bar. Second combination, when B is 0. Now when B is 0, there are two combinations, this and this one. Now in both the cases, if I see the output is fixed, it is 1. So if output is fixed, we can write Y is equal to 1. Let's draw it with the transmission gate. This is the first one, connected with B bar. This is connected with B. This is with B bar. Now when B is 1, this will be turned on, connected with Y is equal to A bar. So let's connect this with A bar, and when B is 0, Y is equal to 1. So this is connected with high voltage VDD, and this will be our output as 1. So this is NAND gate using transmission gate. Now let's come across the fourth as NOR gate. So for the fourth NOR gate, again this is the complement of our OR gate. So we can write this as A plus B whole complement. So 0 plus 0 0 is complement 1, 0 plus 1 1's complement 0, 1 plus 0 1's complement 0, 1 plus 1 1's complement is 0. So this is our truth table for NOR gate. Let's come across the conclusion. When B is equal to 1. Now there are two combinations, this and this one. So if you see when B is 1, if I see the output is 0, fixed output. So we can write Y is 0, and second condition when B is 0. If you see when B is 0, for these combinations, here the output is 1 and here output is 0. Now it's different, it's not fixed. So we can come across A. So if here A is 0 and it is 1, so it will be complement. Here 1 0, again complement. So you can write y is connected with a bar. So let's draw schematic. This is b bar, this is b connected with a complement, and this is our b bar. So when b is 1, no, we know that this is turned on, so connected with 0. So ideally we can connect this to ground. And when b is 0, y is equal to a bar, so this is connected with a bar, and this is output y. So this is how we implemented NOR gate using the transmission gate. Now we are left with two gates, one is XOR and one is XNOR. So let's draw them. So here the fifth one is our XOR gate. It is nothing but a comparator one. So we'll first draw its truth table. A, B, this is Y. So 0 1 1 0 1 1. Now we know the truth table of XOR gate as when the inputs are different, output will be 1, and when the inputs are same, the output will be 0. So by that case, here both the inputs are same, output is 0. Here they are different, 1 different, 1 1 1, it will be 0. So let's conclude. First, if the control input is 1, that is when b is equal to 1. If you see, when b is 1, here the output is 1, and again when it is 1, output is 0. So it's not fixed. If it is not fixed, it should depend upon a. Let's see, here a is 0, here it is 1. So 0's complement is 1. Here 1, again 0. That means it is complementary. So when b is 1, y will be equal to a bar. Counterpart, when b is equal to 0. Now when b is 0, here output again 0, and here it is 1. They are not fixed. So let's see a. Here a is 0, here output is 0. Here it is 1 1. That means in this case I can write y is equal to a. Let's draw the schematic. So first case, when b is 1, connected with a bar, and when b is 0, connected with a, and this is the output as y. So this is our XOR gate using transmission gate. Now let's come across the last one as XNOR gate. Sure, we have with XNOR gate. It's basically the complement of XOR gate. So we'll reverse the truth table. So here 0 1 1 0 will get 1 0 0, and let's first conclude it when b is 1. If you see, when b is 1, here output is 0, here it is 1. So it seems to be dependent on a. Let's derive this. A0 output is 0, a1 output is 1. So we can write y is equal to a second combination if b is 0. If you see, b is 0, here we are getting 1, and here we are getting 0. They are not fixed. That means it should be complement or same. Let's see, a0, this is 1, so this is complementary. A1 0, this is complementary. So y will be equal to a bar. So it seems it will be a simple conversion or inversion of our XOR gate. So this is again the same one. This is p bar. So in this case, this is a, and this is a bar. So this will be our implementation of XNOR gate using transmission gate. So I hope you understood the concepts of how to implement logic gates using the transmission gate. Thank you.